In this video, we will be focusing on the first law of thermodynamics and how we can apply it to different kinds of processes, especially an isothermal process. So what is first law of thermodynamics? We already know that energy is conserved and it can be changed from one form to another. So let's just focus on the first part of it, that is energy is conserved. What does that really mean? So what it means is that energy of a system will remain constant if no external influence interacts with that system. But what if some kind of external influence does interact with our system? What then? So for a closed system, go back and look at what a closed system is. So for a closed system, the only ways energy can be increased or decreased is through transfer of energy, either through work or heat. So now we can actually write it in terms of an equation, which is this. And over here, what this means is that the change in the amount of energy contained within the system is equal to the net amount of energy transferred through heat into the system minus net energy transferred through work out of the system. Okay, so we have to be careful with these sign conventions here. And now let's just focus on this first term here, which is change in the amount of energy, because that takes us to the second part of the first law, which is that energy can be changed from one form to another. So in order to look at that, let's just first of all look at this example of a tennis ball that is moving through air now. So intuitively, we would know that, okay, this tennis ball would contain kinetic energy due to its motion and potential energy because of its position relative to other systems. But what we know is that this ball, in fact, contains more kinds of energies on a microscopic level, because within this ball, it's actually made up of tiny particles. It's actually made up of molecules. And these molecules are then made up of atoms and subparticles that are held together by bonds. And now these molecules and atoms and bonds only exist because of some kind of energies, right? So that means that besides kinetic energy, besides potential energy, there must be some other kind of energy as well that exists within this ball. And now it can be kinetic energy in the form of, let's say, the translational motion of these molecules within the ball. They're moving around. Or it could be the rotation of these molecules, or it could be the vibrational energy of these molecules. It could be the energy that exists between the bonds in the form of intermolecular forces, intermolecular bonds or something. So the sum of all of these kinds of molecular kinetic and molecular potential energies is called internal energy, and it's represented by U, basically. Basically, internal energy is energy associated with the atomic motion. So what we are saying is that if this ball was not even moving, let's say if this ball had zero kinetic energy, it had zero potential energy, there would still be some kind of energy that would exist within this ball, and that would be represented by the internal energy. Okay, so instead of writing this like in terms of E2 minus E1, we can write it in terms of this expression. Okay, we can expand it into this. And now, usually in thermodynamics, we are more concerned with changes in the internal energy of the system instead of looking at the kinetic or the potential energy changes. So basically, what happens is that these two terms, kinetic energy and potential energy, these two go out, and we are left with this equation. Okay, so a simple example of this equation could be in terms of a piston cylinder arrangement here. So we have a piston, this is moving, we have a cylinder, and we have a gas in here. Okay, so this cylinder is filled with some kind of gas. Okay, this is the system, this is a piston here, and so we have a gas here that has a certain volume at a certain pressure. So what that means is, so we're just looking at this initially. This is already here, and now what that means is that this gas already exists at some certain volume at a certain pressure. Okay, so if we're looking at something called a PV diagram, where P represents pressure and V represents volume, and if this gas already exists at some pressure or some volume, it has some kind of volume, it exists at a certain pressure, it could be anywhere on this. So let's just say that it exists here, okay, at the initial state. So this becomes basically state 1 for our system. And now what we're doing is that we're letting this gas expand quickly. And because of this, what happens is that now the volume of the system is going to increase, right? It's expanding, this gas is expanding, so it occupies more volume now. And so that means that the volume increases at the same time the pressure of the gas decreases. And if we were to look at this system now in the PV diagram, we're saying that the volume has increased. So that means that it should move in this direction. And we're also saying, though, that the pressure has decreased. So that means that we should move in this direction. So from this state 1, we would be, let's say, arriving somewhere here, let's say, okay, after the expansion. And now this is going to be represented as state 2. So our system has gone through this process 1 to 2, from state 1 to 2. And how did it do that? Some kind of work has been applied on the system, okay? And that has allowed these other interactions to take place as well within the system. And we have basically completed this process for this piston cylinder arrangement without even having to look at kinetic energy or the potential energy for the system. Okay, so another thing that we need to remember is that the temperature of this gas might increase or might decrease as well. And what is temperature? Temperature is just a measure of the average kinetic energy of the particles, the average kinetic energy of the particles that are within this gas, okay? So for ideal gases, this means that internal energy is basically directly proportional to temperature. So what this means is that the more the temperature increases for an ideal gas, the more the internal energy of that ideal gas is going to increase as well. So if the temperature doubles up, the internal energy is going to double up as well. If the temperature lowers, the internal energy is going to lower by that same proportion as well, okay? So higher temperature means more internal energy within the system. Lower temperature means less internal energy within that system. So when we write this equation, what we really mean is that the change in the internal energy of the system is equal to the energy transferred to or from the system as heat minus energy transferred to or from the system as work, okay? And now we also need to look at this expression, because when we're talking about thermodynamics, and especially when we're looking at this piston cylinder arrangement, we've arrived from state 1 to state 2, we've completed this process. And what we can say is that according to calculus, the area under the curve here is going to describe the work that has been done for the system. This represents the work done in terms of pressure and volume. We are basically integrating it over the entire volume from V1 to V2. And in this way, we can write work in terms of pressure-volume relationship. And now there are different possibilities. Say we're going to look at 3 or 4 easier or to understand examples. First is that say the volume is not changing here. The volume stays constant. What that would mean is that your term here, PV, this is going to be equal to 0. And because of that, the work done is going to be equal to 0. And now because the volume was not changing, it was constant, so it's a constant volume process. Or in other words, we can call this process as an isovolumetric process. And the only way for this system to interact with its surroundings is through heat transfer, and that means change in temperature too, in terms of either changing the internal energy or in terms of having heat transfer for the system. Okay. So the second instance is that let's say that we are looking at a system for which Q is 0. Okay. So there's no heat transfer that is taking place. And because there is no heat transfer, so that means that the only way processes could occur, the process could occur is that the internal energy changes and it is converted exclusively into work. Okay, this is called an adiabatic process. And then the third example is a special case for which we basically have no heat or work interactions between the system and the surroundings, and that is called an isolated system. Okay, so no heat interactions taking place off the system with the surroundings, no work interactions taking place, and that is an isolated system. Don't worry about this direction. It's actually not moving at all because it's an isolated system. No work can be done on it, so just don't worry about this arrow here. And now the fourth one is another instance that say you have internal energy is not changing here. Okay. Or in other words, what I can say is that let's look at it from a different angle. Let's say that we have a constant temperature process, and a constant temperature process means that it's an isothermal process. So for an isothermal process, we are saying that it's a constant temperature process, so the temperature is equal to constant, and that means that there is no change in temperature either for this process, and that means that delta T will be equal to 0. And now because delta T is equal to 0, we've already said that internal energy is directly proportional to the temperature for ideal gases. So that means that if delta T is equal to 0, then delta U should be equal to 0 as well. So from the first law, we can simplify this equation, and what we can say is that the work done on this system should be equal to the heat that is removed from the system. Okay. And in terms of the ideal gas law, which is PV equals RT, or if I was to, because I'm going with specific volume right now, if I wasn't going with specific volume, it would be PV equals nRT. Because the temperature is constant, R is already a constant, so PV is going to be equal to constant. Okay. Or we can write it in terms of P equals constant by V, where V is the volume. And now if we were to represent this equation onto the PV diagram, what this shows you is that this is basically y equals 1 by x, of the form 1 by x, or actually you should replace 1 by some kind of constant in here, c, because you don't know what the constant is right now. And by mathematics, we know that an equation of the form of y equals constant by x can basically be translated graphically into something like this. It's kind of straight, but don't worry about these here. Okay, so again, the area under the curve represents work, and the other thing to notice is that PV is equal to constant. That means that change in this is constant too. Okay, so what that means is that if I had some kind of pressure here and some kind of volume here, if I multiply these two, it should be equal to the term that I would get if I multiplied the pressure here and the volume here. Or if I multiplied the volume here and the pressure here. Okay, this is what it means. The other thing to notice is that because we already know that the volume is increasing in this direction, but our process is from this state to this state here. So what we can say is that if the volume is increasing, that means we have a process of expansion here. Our gas is expanding. So volume is increasing in this direction, so that means an expansion process would be of this direction. Okay. Whereas if we were talking about a compression process, so what does compression mean now? That the volume is decreasing, and a decreasing volume is represented on this graph in this arrow direction, and that means that this same curve should have a completely opposite direction. Okay, so this is how we can represent an isothermal process on to a PV diagram. And remember that first law is true and applicable for every process. Every process obeys the first law of thermodynamics. So you can go ahead and write this equation and work out the expression for every kind of process, whether it's adiabatic, whether it's isovolumetric, whether it's isobaric. All of these follow the first law of thermodynamics. So now if you were to go and practice this on your own, I'm leaving this problem here for you. If, say, you have a piston cylinder arrangement and the process is being represented by this equation, which is PV to the power n equals constant, it's called a polytropic process. So you have the initial pressure given to you, which is P1 here. You have initial volume given to you, which is V1. You have the final volume given, which is V2. So you have to find out the work done for this process in kilojoules if n had a certain value, and x could be of the form, let's say, 1.5 or something like that. And you also have to draw the schematic for this specific value of n onto the PV diagram, and also make the piston cylinder arrangement schematic too, just so you have an idea of what this process would look like.